Hi all, this is Donald Winter and I'm doing the Chem Processing MATLAB problem for Engineering 1331. I'm just going to take you through a couple slides before we get to the actual MATLAB. So the purpose of this was basically for us to take an equation, a stoichiometric equation that is balanced, and let it go through a reactor and then be cooled and purge off a given pure substance and purge off another pure substance and then recycle the rest and start all over. This can be applied in the engineering field because that is basically what we do. Is you have a certain amount of chemicals and you're trying to make it the most efficient way to get the X amount of chemicals that you're needed. Some equations that we need, basically the first one is what is going in must come out. The second equation is the actual stoichiometric equation that we use for ammonia. Then the enthalpy and the energy balance equation, basically those are both going to be used at the end of the MATLAB, and it's used to maximize your cost or minimize your cost and maximize your output. Some limitations that we were using, there's only 1 mole being added to the system every time. In the real world, it'd probably be much more going on, bigger volume basically. How long the process runs, we basically made an assumption that we want it to run when the amount of output, the pure substance that are going output, are smaller than the input. And then there's a cooling chamber, and we had to assume that the cooling chamber was under pressure due to the fact that our chemical does not condense at the temperature that it was given to us. I'll get to that later. So after our limitations, we can get to our MATLAB, actually our algorithm. So basically our initial thought was, okay, per the request of the assignment, we are going to have the user input 3 different variables, and then those variables are going to be mole fractions. These mole fractions have to be less than 1 because it's a fraction. If it's 1, it's going to be basically 1 mole is coming in, 1 mole is going out of one section, and that's impossible. Matter cannot be created nor destroyed. So you can't have a pure substance of all 3, basically. So we have the user input it, all 3 of them. If it doesn't work, it's going to send them back to the top, and then go to the next one if it does work, and so forth, so on. And then it's going to run the code, and then we're going to have some values of purged, some values consumed, and then the ammonia that we are trying to find. And then we're going to graph these variables, and then we're going to try and maximize our cost, minimize our cost, maximize the efficiency of the system, and then ask the user if they want to do it all over again. And if they say yes, it's going to run back to the top. That was what our first thought process was going in. Here's our actual code. I'll walk y'all through it before we run it. So first task was just have them input the mole fractions. So basically it's while it's less than 1, if they put anything above a 1, it would give them a warning and tell them that it needs to be between a 0 and a 1, and then it would allow them to do it all over again for all 3 of our inputs. And then we have this function, and I'll show you the function, and this is basically where all the magic happens. So we have these equations. Okay. Let's see, we had all of these equations, these 6. Okay. And then from those equations, we pulled N1 and N2 and solved for them. So we can solve for the whole cycle. Once we did that, we basically initialized that 1 mole was going in. have the user input their inputs. It's going to create 1 mole no matter what, and then run the system 1 time. So basically each section here this is when it goes through the reactor, and this is when it goes through the cooling, and then this is when it is recycling. So after the first initial time that we turn the system on, it's not going to be recycling anything. It's basically going to go through the system, and then we're going to have things that need to be recycled. So we initialized everything. So when we went in to do the cycle, it would create these equations. Basically, after it ran the first time, this stuff that was up here, after it ran the first time, those variables became this, and then they went into these equations, and so forth and so on. And then we did a count just basically to show how many times it runs. So let's go back to the code. After we get done with that, we wanted the user to see what was going on. So we did some plots. So in these plots, we let their inputs vary from 0 to 1 so they can see how to optimize the system. So we could see how to optimize the system. And that is basically what all of these are. After we optimized the system, we made all of the graphs overlap, and then basically showed like an f-printf statement that gives what the best mole fraction for each one is to create the maximum output. That's what those are. And then calculating the cost to run the system. These were where we used those last 2 equations I showed you earlier. We had the user re-input everything per the request of the assignment. I would have liked to have used the stuff from their inputs from the earlier section, but that wasn't the request for the assignment, so here we are. So let's go to our cost. Pretty straightforward. We're going to have the heat capacity, have the specific heat, have how much it costs. The variables, so these are the equations that we used in the beginning to make all of this work. The change in temperature in degrees, the flow rate of the purge, the flow rate of the ammonium leaving, the flow rate of the extended leaving. So these are basically all the equations from before, just divided together to create these. And then we're going to try and change our kilowatt per hour, kilomole per hour to mole per hour. Pretty straightforward, guys. Get our molar percentages of all of them. Calculate the joules. And then the cost to cool it. So let's get to running this. So we're in the first section. Enter the mole fraction of the inert gas. We're going to go 0.5. Let's just do 0.5 straightforward. We get these values. Then our graphs are going to plot. So this is what I was talking about when I said we let the variables that they inputted vary from 0 to 1. So we got these graphs and polyfitted them to get the lines, the best fit curve for them all. And then once we got all 3 of these to graph, we overlaid them to see where it can be optimized per the mole fraction given. That's what this graph is right here. Okay, after we do that, we'll go to optimizing the cost. We're going to have to re-enter. Let's just use 0.5 again. Okay, our cost is 157.23 per hour. Would I like to recreate a menu? Would I like to re-input the values? Let's go yes. Let's try it again. Let's go 4, 3. Oh. Okay, unexpected MATLAB operation. Okay, this is because I put 4 inside of a mole fraction. See, so our code did not continue to run there. It actually just ended it right there. So we're going to do that again. Oh, looked at 158.50 per hour this time. Alright, so I've run that one twice. Now let's go back to the graphs. Let's enter these in again to give y'all some variation. Oh, so this is a way better line. So you can see there is some jump in these curves here. But overall, we hit exactly what we want to hit here on this graph. Because you can see there's a definite best maximum output and input right here. And then we have it down here. It's basically showing you what the maximum amount of moles produced would be, and then where the graph basically have an F-graph statement showing what the best place in the graph. So from this, guys, I just want you all to see that this is a very simple equation, a very stoichiometric. This is a very easy stoichiometric equation that we can apply later on to bigger equations. Thank you for watching.